Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to your online lecture series of W314 Measurements and Instrumentation. This is the first lecture of your online lecture series, the week 9 lecture 1, and it would be the lecture number 25 in your regular course. And in this lecture we are going to discuss the operational amplifiers. So let's get started. In today's lecture we are going to discuss about what are op-amps, derive their transfer function, and discuss their basic configurations and how do they work, and then we'll solve some examples related to their applications. So let's start with what actually is an operational amplifier, or an op-amp as we call it. An op-amp is a 3-terminal device usually. The rest of the two are for power supply. So it has 2 inputs and 1 output. One is a non-inverting input, the second one is an inverting input, and the third one is the output. So an ideal op-amp has some characteristics that I'll list down here. An ideal op-amp has an infinite gain. It has infinite input impedance. It has a 0 output impedance. Because it has an infinite input impedance, no current will flow through the inputs, because the inputs will act as an open circuit. Then a general rule describing the operation of an op-amp states that an op-amp will do everything it can to keep both its inputs at the same voltage level. Now, what can an op-amp do? The op-amp will change its output so that to make its inputs equal in voltage magnitude. But if we don't have any connection or any link developed between the output and the inputs, it cannot maintain that general rule, or it cannot implement that general operation. So in case of open loop, this rule number 5 will not be applicable, but we will see that in which cases this rule number 5 will be applicable. So an op-amp will do everything to keep its inputs at a same potential. Now we can also assume as a general rule that these two inputs will be at the same potential if the op-amp is not operated in an open loop configuration. What is an open loop? An open loop is when there is no feedback and no link or no connection between the inputs and the outputs. And as you can see right now, right here in this op-amp, there is no connection between the output and the inputs. So this is an open loop configuration. The transfer function of this open loop configuration is V positive minus V negative into gain is equal to V output. Now if this gain is infinite, it doesn't matter how much was the difference between V plus and V minus. So this delta V doesn't matter. Even a very minute difference between these two positive and negative inputs will result in an infinite output if it is multiplied by infinity. But the output cannot be infinite. So the output will saturate to the supply voltages, the positive and negative supply voltages. Obviously, it cannot go beyond that. It cannot produce its own energy or its own voltage. Now, this is the ideal operational amplifier. But we know that in reality, an infinite gain is not possible. So, it must be of some value, maybe a very, very high value, but infinity is not possible. So, yes, in reality, this gain is not infinity, but the gain is very, very high and is nearly more than 100,000. Now, 100,000, 200,000 or 300,000, these are finite numbers. And when multiplied with any other finite number, finite del V, it will result in a finite V out. And now you can see that if my delta V, let's say my supply voltage was 10 volts. So the V out can go maximum up to 10 volts because it will saturate at that point and it cannot go beyond the supply voltage. So to reach 10 volts, my del V should be 1 into 10 raised to power minus 4 at max to reach 10 volts or below that. So my del V should be less than 1 into 10 raised to power minus 4 volts and greater than 0 volts to keep my V out between 0 and 10 volts, because 1 into 10 raised to power minus 4 into 100,000 is equal to 10 and 0 into 100,000 is equal to 0. So yes, you can still achieve amplification in an open loop configuration, but this puts great limitations on your input voltage. 1 into 10 to the power minus 4 is 0.1 millivolts at max. Usually, what kind of signals you are trying to amplify? Some signal from the microphone, sound, sensors, any kind of sensor or any other voltage. 0.1 millivolt is usually not the voltage level of your inputs. It can be in few millivolts or few hundred millivolts or even few volts. It may be around 0.1 millivolt at certain times in special particular cases, but not generally. So it is not advisable to use the operational amplifier in an open loop configuration for amplification purposes. It can be used as a comparator, but we'll come back to that later. So how to solve this issue? How to solve this limitation on the input voltage of the operational amplifier to utilize its amplification property and use that gain of an amplifier to amplify our signal? What we can do is we can reduce this gain. What if we reduce this 10,000 or 100,000 to 100? What would be the range, allowable range of the input before the output is saturated? Now in this case, 0.1 volts, right? Because 0.1 into 100 is equal to 10 and V out would be 10 volts and that would be saturated. So we have improved the limitation on our input voltage by a factor of 1000 by reducing our gain by a factor of 1000. Now the question is, why do we want to reduce the gain? The more the gain, the better it is, right? It sounds like that the better the amplifier if the gain is higher. Not always, because sometimes as we saw here that our input signal was not in this range and it was being limited by this very, very high gain of the amplifier that we didn't even need. So in some cases we have to reduce our gain according to our applications and our actual requirements. So how to reduce this gain? The next question would be, we will use this rule number 5, and we will use a feedback with this operational amplifier, a positive feedback or negative feedback or whatever. We will see that what will happen if we connect the input and the output through some feedback component. What would be the effect on the input voltages, output voltages, and the gain? So let's start with a simple feedback circuit like this, positive, negative. So let me connect my negative input to my output directly, and here is my input V in and V out. Now we know that all these 5 rules apply because there is a feedback, right? There is a feedback from the V out to the V in. So now there is some link, some connection, some feedback between the outputs and the inputs. So now this operational amplifier will do each and everything it can by changing its V out to keep its V in positive and V in negative equal. Now let's see what was the value of V in. V in can be any voltage V in. Let's denote it by V in or V positive. We are supplying this voltage. There is no other voltage in this particular circuit that we are supplying except those power supplies, that is just to power up the circuit. But there is just one input voltage that we are supplying. So this means that V plus will be equal to V in. But now we can see that there is a feedback connected between the V out and the V in negative. So when there is a feedback, V plus will always be equal to V negative. Both the inputs should be equal. So V negative should be equal to V in. And as there is a short circuit, V out is short circuited with the negative input, so that would be equal to V out. So this means that V out is equal to V in. We can see here, we have derived this relationship. The output voltage is equal to the input voltage without any gain. So this is a unity gain buffer. What is the purpose of that? We have reduced the very high gain of an amplifier to 1. It is no more amplifying. It is just giving a unity gain to the signal. So whatever signal we are sourcing at the input is traveling to the output without any gain. What's the purpose of this? Does it sound useless? In the first glimpse, maybe. But this particular unity gain buffer is a very important and very useful circuit, because if we see the other 4 rules, the op amp has infinite input impedance and the op amp has no current flowing to the inputs and it has a 0 output impedance. Now this V in will be coming from some source, some sensor or some microphone or anything, and that supply will have some output impedance, right? If I connect any circuit or any other device at its output as its load, this splice load, the circuit will become like this. So this would be the this would be the Z out of the source, and this would be the Z in of the load. And if there was V in coming here, only a fraction of V in will be delivered to the next circuit actually because of the loading effect, Z in over Z in plus Z out, right? So it will be divided. But in this case, we know that the input impedance of this operational amplifier is infinite. So what if this Z in is not there? It is an open circuit. So it will be infinity, and using L'Hopital rule, it will become 1 into V in. So there will be no degradation or no attenuation in the input voltage that we are trying to supply to our system. So that is why we call it a buffer. It is reducing, or it is virtually eliminating the effect of loading. So if we want to connect two systems together and we want to reduce or eliminate the effect of loading, we include a unity gain buffer between our input and our system. So now this V out can be supplied to any other system, and as we know that the output impedance of this op amp is 0. If we see here, this output impedance will be 0 and there will be no effect of loading whatsoever on this output. So even if I connect something to this output, some load to this output, the actual value will not be affected and all the current will flow from this load because here the impedance is 0. So this was the most basic feedback circuit for an operational amplifier, in which we just eliminated the gain, we reduced the gain from whatever value it was to 1 and made a unity gain buffer, and we saw that the rule number 5, where the op amp was changing its V out so that both the inputs are equal, is actually implemented. Now moving on to a little bit more complex feedback circuit, and that is an inverting amplifier. In an inverting amplifier, again we have a positive input, a negative input, and an output. But in this case, okay, let me switch the positive and negative terminals here, negative and positive, right? Let's put this V positive to ground and give our input through a resistor to this negative terminal, and then connect a feedback with the output through a resistor, and this is R2, this is R1, and here is our V in, and this is our V out. Now going to the basic rule, both the positive and negative terminals are getting some sort of supply voltage, right? V in is supplied to the negative voltage through a resistor, and a 0 volt or a ground is applied to the positive input directly. Which effect would be dominant? This one. A 0 is definitely here. We don't know the voltage on the negative terminal at this point. At this point we don't know the terminal voltage right now, but we are for sure that at this point, at this positive terminal, there is a 0 volt, right? We all agree to that. Now if a 0 volt is here, there must be a 0 volt at the negative terminal also, because there is a feedback connected between the V out and the V in. So there must be a 0 volt, and the current flowing in or out of this positive or negative terminal should be 0. So some current is flowing I in, and some current is flowing here I F, right? Can we write an equation here? V in minus 0 over R1 is equal to I in, and V out minus 0 over R2 is equal to negative IF. But as we know that at this point no current is leaving from here, so I in must be equal to IF. In this case there is no other path, so all the current flowing from this source through this R1 should move on to through this feedback resistor to the V out, and here the current will split, but we don't care about that. So let's equate these two equations. V in over R1 is equal to negative V out over R2, which means that V out is equal to negative R2 over R1 into V in. Now you see here the input voltage is being multiplied by a factor, and that factor is the ratio of our feedback resistor to the input resistor. And now this factor is the gain of our amplifier. So now we have a tunable gain. We can set the value of R2 and R1 to whatever value, and based on their ratio we can get whatever gain we want. As far as the V out is within the saturation limits. So this is a very powerful circuit that can be used to amplify our input signal and give a gain that we want. This configuration is called an inverting operational amplifier because of the two things. Number one, because there is a negative in the gain, so the input is inverted at the output. There will be a phase shift of 180 degrees. And secondly, the input is actually directly applied to the inverting terminal, so giving the name of an inverting operational amplifier. And now we can actually calculate that if our V out is equal to this value, this will mean that a 0 is here at the negative input terminal to make it equal to the positive input terminal. V out is this value. If you put this in this equation number 2, you will find out that there must be a 0 at the negative input terminal. So what's happening? What the op amp is actually doing? We supplied an input voltage and we connected a ground, a 0 volt, to the positive terminal, and the op amp produced a V out equal to this value to make sure that there is a 0 at the negative input terminal also. And what had to be the value of V out in that case to make it equal to 0 was this value of V out. What we did was, for our convenience, we wanted to find the value of V out in our case, and we assumed that there must be a 0. But what actually happened was the V out was already produced by the op amp based on the inputs to make this V neg equal to V positive and equal to 0. We just didn't know what was the value of that V out produced by the operational amplifier. So we wanted to know that what this operational amplifier did, what magnitude of the V out was produced by the operational amplifier to keep these two inputs equal. We just wanted to investigate and find it out, and we did it using this derivation. So this is the start of your operational amplifiers, and next we are going to study about the non-inverting configuration in the next section. Alright, so we have derived the relationship of V out and V in of an inverting amplifier and we have come to the conclusion that we can give any gain within the limits of the operational amplifier by setting the values of this R2 over R1 ratio. Few things that we have to keep in mind while designing our operational amplifier circuits is that this gain that we are giving to our inputs should and must not exceed the V out from the supply voltage. Otherwise, there would be a saturation and this relationship will not hold. The second thing is that while choosing the combination of this R2 and R1, we have to be very careful that how much current, how much I in and I out and IF are being supplied by the op amp, and the amount of current that is flowing through these resistors and through this op amp. Thus far we have been considering only the voltages, but now we have to consider the current as well. So let's do an example and let's see what happens if we choose unrealistic values of an operational amplifier. So let's say we want to give a gain of negative 4.5 to our input, any input that is coming to the inverting input of the operational amplifier. We want to multiply it with a gain of 4.5. So as we know that the formula of the gain is negative R2 over R1. So what all we have to do is we have to set the ratio of R2 over R1 equal to 4.5 to achieve this gain. What if we choose R2 equal to 4.5 ohms and R1 equal to 1 ohm? This means that R2 over R1 will be equal to 4.5. But let's see how much current will be flowing through this operational amplifier, and to find the current we have to know that what was the value of our input. So let's assume our input was Vin was equal to 2 volts, and when multiplied by 4.5 our V out would be equal to negative 9 volts. 2 into 4.5, and the current that has to be supplied by the operational amplifier would be determined by this V out over RF, right? That should be equal to the current. So let me write it separately. So the I out that has to be supplied by the operational amplifier would be equal to V out over RF, and that would be equal to 9 over 4.5, and that comes out to be negative 2 amperes. This is a very high value of current, and in the operational amplifier data sheets you will find out that the op amps can usually supply current in the range of approximately up to maybe 10 milliamperes, or in some cases 20 milliamperes, or even 1 milliampere. The op amp cannot supply a current more than the maximum saturation value that is mentioned in the data sheet. But if we choose our resistors of these values 4.5 ohms and 1 ohm, those are unrealistic values to provide the gain of 4.5. that result in a current of 2 amperes to be supplied by the op amp, but the op amp cannot supply a current of 2 amperes. So what would happen? What would happen in this case is the op amp would try its best to supply as much current as it can, but it could only apply, let's say 20 milliamperes. So it would saturate at 20 milliamperes, and then how much voltage you would be getting? The V out would become 20 milliamperes into 4.5 ohms, and that is equal to around you can say 990 millivolts. The output will not go beyond this point. So your input was 2 volts, your output would be 90 millivolts. Even if you selected your resistances, the ratio of your resistances to be 4.5, it is giving an attenuation rather than a gain to your input voltage. Why? Because the current was saturated in this case, not the voltage now. So we have to be very careful while selecting the combination of these resistors. Yes, in some cases you can give even attenuation to your input voltages. An amplifier is a circuit that provides gain. The gain can be more than 1, the gain can be less than 1. In cases of less than 1, we call it attenuation, but still it is a gain of, let's say, 0.1. So you can give a gain of 0.1 to your input voltages, and that is very much possible using an op amp. But we have to keep in mind that this V out should be within the saturation or the supply limits, and the current should be within the current limitations of the op amps, that how much current can be supplied continuously by the operational amplifier. So these are the few things that need to be kept in mind. And now we are actually starting towards developing of analog signal conditioning circuits using these operational amplifier circuits. So what you will be doing is, you will be using your signal from your sensor or the transducer, and you will be converting it to the to different levels, and you will be implementing some different equations on that input, and you will be converting the type of input to another type of input. For example, you will be converting a change in resistance to a change in voltage, or a change in voltage to change in current, and vice versa, using these operational amplifier circuits. So now, after completing the inverting amplifier, let's move on to the non-inverting amplifier. In non-inverting amplifier, the input is taken at the non-inverting terminal. Like here, the input is directly taken at the non-inverting input, and the inverting input is now grounded, but the feedback is still connected at the inverting input. So now you can see that we are still using a negative feedback, but rather than supplying our input at the inverting input, we are supplying it at the non-inverting input, and we have grounded our inverting input through a resistor. So here in this case, again, let's say this is R2, this is R1, and this is Rin. Now let's try to find out the relationship between the V out and the V in using the 5 rules that we have established earlier. The first rule, or the fifth rule that we discussed there, but we are going to implement it as the first rule in this derivation, is that the voltage at these terminals V plus and V minus should be equal. What actually happens is, again, that V out would change so that to make these two V plus and V minus, these two voltages equal. So this means that V plus is equal to V in is equal to V minus. And now again we can find out the currents, the current flowing through these resistors, because no current is flowing in or out of both these terminals. So the current I that is flowing through this resistor R1 will flow through this resistor R2 through the negative feedback and will reach the V out. So let's find out the currents. I1 I can say, and I2 here. I1 is equal to negative 0 minus V negative over R1, and I2 is equal to V negative minus V out over R2. And as I1 is equal to I2, this implies that V neg over R1 is equal to V neg minus V out over R2. And now this V neg is equal to V in, as we already know, because the voltage at both these terminals is equal. So we can see that V in over R1 is equal to V in minus V out over R2. To find the relationship between the V in and the V out, we can rearrange this equation and we get V out is equal to 1 plus R2 over R1 into V in. Now you can see that the gain actually is this expression, because the gain is V out over V in is equal to the gain is equal to 1 plus R2 over R1. So this is the expression of gain for the non-inverting amplifier. What is the advantage here? How is it different from an inverting amplifier? The first one is that we are getting a positive gain. We are not getting a negative gain, and that means that the phase of our input and the phase of our output are in sync. The phase of output is not shifted by 180 degree as compared to the V in, just like in case of an inverting amplifier. So a non-inverting amplifier does not invert your input waveform and provide a positive gain. The second advantage is, we can see here that this input here, V in, is directly connected to the positive terminal, to the input of the operational amplifier. What does this mean? The input impedance of this operational amplifier is infinity. So this operational amplifier will not act as a load on this V in, because it is directly connected to the input. But in the case of an inverting amplifier, as we can see here, this V in is connected to the negative terminal or the input of the operational amplifier through a resistor, through this resistor R1. So now the op amp has an infinite input impedance. Yes, we know that. But this system, this configuration, including this R1 and R2 resistors, the non-inverting configuration, the inverting configuration does not have an infinite input impedance. Its input impedance, as seen by this input voltage, would be equal to R1. So this configuration will act as a load on your V in, not this op amp, this configuration itself. So that is the second advantage of a non-inverting amplifier, that your input is directly connected to the input terminal of the operational amplifier. No loading effect. But what is the disadvantage? The disadvantage is that in case of a non-inverting amplifier, you cannot have a gain of less than 1, because here, if you note that the expression of gain is 1 plus R2 over R1, so that 1 is being added. The minimum gain that you can get from this configuration is 1. If you make these R2 and R1 such that this expression becomes 0. And what was that case? We already discussed that. That was a unity gain buffer. If we go further up, here the input is directly connected to the non-inverting terminal, and the negative input is connected to the output without any resistor, and here there is no resistor. So this is R2 is 0 and R1 is non-existent. There is no ground. this expression will become equal to 0 and there will be a unity gain, just like in this derivation that we found out. So a non-inverting input with a non-inverting amplifier with a unity gain is a voltage follower circuit, a unity gain buffer. The second name of this configuration, the unity gain buffer, is a voltage follower circuit. So now we have discussed the three basic types or three basic configurations of an operational amplifier. And now, based on the understanding we developed in these configurations, we will try to build up and we will try to derive the expressions, the relationship of output with input of some more complex configurations that we will be using